I start.
Just F5.
Yeah. Testing. Good. Okay. Good afternoon. I hope you all had a good lunch. My name is Anders Ringbom, and beside me we have also Romano Planteda from PTS. And we will share this session named Atmospheric Background of Radio Xenon. We have 3 talks, and then we have a discussion also scheduled for 15 minutes, and then at 3 o'clock we have the poster preview session. So we can go right on with the first speaker, which is then Andreas Bollhofer. We talk about identifying civil xenon emissions from source to receptor. Please, Andreas.
Thank you, Anders, for your nice introduction. I will be presenting results from several studies that were conducted over the past approximately year and a half at BFS, the German Radiation Protection Office in Freiburg, and by our colleagues at Hamburg University, and also with our Belgian colleagues from SEK-CEN, the Royal Meteorological Institute, Ghent University, and the Institute for Radio Elements in Fleurus in Belgium. To briefly define the objective of our study, I'll show you this map. You've all seen that before. It shows the noble gas network of the IMS, and presently 25 of the 40 planned noble gas stations are certified. RN33 is one of them, and it is the only noble gas station in Central Europe. We are running a SPELEC system, which is housed in the building that you can see on this slide here. The figure to the bottom shows the Xenon 133 activity concentration data in microbecquerel per cubic meter, just to show from 2017, so from the 1st of January up to about a couple of weeks ago. So why do we measure xenon in the atmosphere? Whereas the waveform technologies in the IMS can provide clues to the location of a presumed explosion, only the detection of radioxenons in the atmosphere allows to unequivocally identify the nuclear nature of an explosion, and thus providing the so-called radioactive smoking gun evidence. The peak that you can see at the bottom there, of course, is not related to a nuclear explosion, but to civil sources, and these civil emissions do impede on the radioactive smoking gun evidence and the verification capability of the IMS. So what are the civil sources of radioxenons? So the radioxenons are fission products. They, as I mentioned, they are emitted through nuclear explosions, and the civil sources are nuclear power plants and research reactors and medical isotope production facilities. As you can see here, this shows the estimated daily emissions from single sources in blue and global annual emissions in red. And as you can see, nuclear power plants emit about 2 to 3 orders of magnitude less xenon 133 per day compared to MIPFs. However, because there's only a handful of MIPFs and more than 400 nuclear power plants, the estimated global annual emissions are only one order of magnitude different. Interestingly, the daily emissions from a typical medical isotope production facility is similar to the amount of xenon 133 emitted by a nuclear underground nuclear weapons test. This picture here shows the multitude of xenon sources in Central Europe. So all these radiation thresholds basically indicate a nuclear power plant or a research reactor or similar. And all these influence the atmospheric xenon levels at RN33. Unfortunately, the same is true for JP38, which is one of the closest stations to the DPRK test sites, which is shown up here. So it's surrounded by nuclear installation, and as I mentioned, this hampers the verification capability of the IMS system. So when I first started working with the BFS 5 days later, a nuclear weapons test was announced at the 6th of January, just as an example. And I was sort of introduced to the theme of CTBTO and was waiting with all the CTBTO scientists and my colleagues in Freiburg for the smoking gun. And then on February 17, the elevated xenon-133 activity concentrations were measured at JP38, but no other isotopes were above the MDC. So that's the peak shown here. However, when you look at the previous year, you can see that these detections here, they are nothing in particular special and appear from time to time. And these ones here were definitely not related to any nuclear weapons tests. So the CTBTO is investigating, of course, how to better characterize the civil xenon emissions. PNNL and Judah is going to talk about that later. They are working on this. And also the IAEA have initiated a project about 2 years ago. That's the CRP project F23031. And Germany and our Belgian colleagues are, as part of this project, involved in studies regarding stack monitoring, xenon environmental monitoring, and atmospheric transport modeling. And the objective is to better understand, or to find ways to better understand xenon civil background. I'm now going to present some preliminary results from our studies. Firstly, I'm going to talk about the stack and near-field monitoring that we've done so far. So we've got a master's project together with the University of Hamburg and the German Radiation Protection Agency, where we are developing and testing a compact spectrometric stack monitoring system to characterize emissions and compare those emissions with those measured by the IRE system. They use a high-purity germanium detector. This is the way this stack monitoring system looks like. It's a cadmium telluride zinc telluride detector. It's got the size of a thumb, approximately 1.5 cubic centimeters volume. It's connected to a Raspberry Pi computer and got integrated electronics. It's very compact. The energy usage is very low, and it's got a reasonably good full width at half maximum of 2% at the cesium-137 line. We also investigated, or started to investigate in a pilot project, the sensitivity of compact spectrometric systems, so that's lanthanum bromide and cadmium zinc telluride detectors, for use as xenon environmental monitors, so not only measure the dose rates, but actually identify the xenon isotopes in the vicinity, in the atmosphere in the vicinity of IRE. Here to some results. This is the system as it looked when we built it, or when we installed it at the IRE stack. So the air from the exhaust, from the stacks coming in here, it's drawn over a couple of charcoal cartridges, and the detector basically sees one of those charcoal cartridges. The same here, that's the high purity germanium detector from IRE. You can see the xenon-133 and the xenon-135 peaks, which are those two, and that's the location of xenon-131M and xenon-133M. And you can see the detector is not very sensitive to these emissions from these two isotopes, partly due to the low emission probability for those two. However, if you integrate over 24 hours, like on day 2, for example, you can see a small xenon-131M peak here, or a small xenon-133M a bit further in the energy spectrum. This is a comparison of the xenon-133 activities measured with the cadmium zinc telluride and the system, the high purity germanium system from IRE. And you can see that the agreement of the two measurements is fairly good. And as a conclusion, we think that the setup of a cadmium zinc detector and a Raspberry Pi is simple. It's a very mobile system. It's small and cheap compared to high purity germanium detectors. It's good at detecting xenon-133 and 135M, but not so good for the metastable xenons. Preliminary data from a pilot project that we only started two weeks ago where we measured xenon 133 and 135, 800 meters northeast of the MIPF, indicate that the lanthanum and bromide detectors are actually quite good in identifying xenon-specific activity concentrations in the air as well. Now quickly to a comparison of environmental data, that's xenon data measured in the environment by the German BFS and atmospheric transport modeling. So this is a Google Maps image of the Fleurus facility. It's located here, about 200 kilometers to the northeast is Trier, and Freiburg is down here, and I'll show some data from Freiburg, Trier, Offenbach and Braunschweig. That these data were collected for the purpose of monitoring for German regulation, that we are supposed to monitor xenon activity concentrations in air in weekly samples by German regulations. The xenon measurements we conduct are either done in a manual system on weekly samples where we use 7 proportional counters, or with a sauna lab system where we measure nuclide specific with a beta gamma coincidence detection system. If you want to learn more about the two systems used at the BFS, this paper here has just been published, so feel free to send me an email and I can forward you this paper. The atmospheric transport modeling was conducted by our colleagues in Belgium. So they had 15 minutes xenon 133 emission data from IRE in Fleurus for 2014. They used meteorological data from the European Centre for Meteorological Weather Forecast on a 3-hourly basis, the model FlexPart at 0.5 degrees horizontal resolution. For the emissions from nuclear power plants, we had quarterly emissions from German nuclear power plants, monthly from Switzerland, France, Belgium and Scandinavian countries. We unfortunately only had annual emission data. And for the emissions from CNL, which sort of don't really matter that much at Schauinsland, we used data from a paper from Ian Hoffman from 2009. And here are the results. Again, it's xenon 133 in microbecquerel per cubic meter measured in air in Trier, Offenbach, Braunschweig and Freiburg. The blue bars show the activity concentrations and the red stapled lines show the minimum detectable concentrations. And when I plot the actual detections above the minimum detectable concentration and compare it with the results from the atmospheric transport modeling, which is shown by the orange lines here, you can see there is times when the agreement is quite good. There is times when the atmospheric transport modeling is orders of magnitude higher than what's been measured at the station. There is times when the atmospheric activity concentration that was measured is by far higher. In particular in Braunschweig, we think this is due to a supplier of nuclear isotopes that's in the vicinity of that monitoring station. But then there is also times where the agreement is actually reasonably good. So as a discussion and future work, just briefly, we think that the ATM reproduces general trends at the stations, but there is periods with higher measured versus modeled data and vice versa, probably or potentially due to misrepresentation of nuclear power plants in a multi-source region like Europe, due to the temporal variability of emissions. So, for example, during ramping up and ramping down the nuclear power plants, the xenon emissions are higher than during the normal operation. Local sources might influence our measurements. The emission data from IRE, there's some uncertainty there perhaps, and of course there's uncertainties in dispersion modeling as well. The averaging reduces the accuracy of the measured and modeled data, and last but not least, we conclude that time-resolved emission data are needed as input into ATM, so that means emission data from nuclear power plants in Germany or the countries bordering Germany are needed for our further studies. We are planning to phase out the proportional counters, only use the sauna system because the activity concentrations are too low these days to be measured reliably with our proportional counters. and continue our collaboration with our Belgian colleagues and do more STEC, near-field and far-field monitoring, and there's a campaign planned in Q3 2017. And we do all that to basically avoid this situation here to happen where the smoking gun can't unequivocally be identified. Thank you.
Thank you very much, Andreas. So we have time for one or two questions. We have any questions from the floor? Can you see? No? Okay. Okay, so if there are no questions, please, thank you again.
Thank you. Thanks, Anders.
So then it's time for the next speaker. That's Jude Friese from PNL. He will talk about source term analysis of xenon called STACS, exploring methods for understanding radio xenon civilian source terms. Please, Jude.
Good morning, everybody. Well, morning. It's morning in my time zone, I guess. I wanted to speak today a little bit about an idea we've been working on, and it's sort of kind of coming together as we're trying to solve this issue of civilian uses of, or civilian emissions of radio xenon. So one of the ideas that we're working on is going to be what I'm going to show here. Does this work? Yes, it does. All right, so I'm going to go over where we're going. I have way too many slides, so I'm going to go through a few of them relatively quick. A brief experiment that kind of was a prelude to the STACS project that we're working on, and then summarize what it up. The previous speaker talked to this quite well. Basically, the whole point is you just have xenon coming from a medical isotope production facility that's being detected in the IMS station. So this is the main issue that we're looking to get further information on to help mitigate this particular issue. One of the main reasons we have this issue is depending on how the production at facilities happen, you can actually have some of the xenon ratios not look like what you typically see coming out of a power reactor. So even though there's more power reactors, the xenon ratios coming out of them are typically unique from nuclear explosions. Medical isotope production facilities, that's not necessarily the case. So what I've shown here is this side is nuclear explosions, this side is reactor, and somewhere in between is usually where medical isotope production stands. So not always can you use isotopic ratios to determine whether it was a civilian source versus something else. So this is why it's going to be key to understand what those ratios are coming out of the civilian sources prior to them reaching the IMS stations. Xenon background, what we have here is a description of some calculations we did of what the issues would be giving different assumed releases. So the top one is the world as we would like it to be. So this is just an annual description of what the xenon is releases if every facility released 5 gigabecquerel per day. And really anything that's green is below the current MDC of our current detector systems. The one below is more akin to what we have today, where the facilities are releasing much more, 10 to the 12 becquerels per day roughly. And again, everything green is not detected, but the red and yellow is detected. It is above the MDCs of our current systems. So this is kind of the motivation why we're going to see these things in the IMS. What can we do to understand what they look like? So the detection technologies, I won't go into this too much, aside from our IMS systems do measure all 4 radio xenons, which means if we're trying to understand source terms, we are measuring source terms at the medical isotope production facility should also include these 4 radio Z-xenon isotopes. So it's starting to say, well, what do we need to understand a source term? IMS, I'm going to totally skip on this. The previous speaker had that. This idea came out of this workshop that we have. It's the WASMIP workshop. So the idea of understanding stack data coming out of the civilian sources came out of this workshop. So this is kind of where we are. More about this workshop is available. There's going to be a poster by my NVAP colleagues later today, I believe. So go check out this poster if you want to know more about what it is. But the point is, this idea is coming out of this workshop to try to see what is possible for measuring things at the source terms. So before we even move forward, coming out of the WASPNet 5 workshop, we kind of said, if we're going to do this, we need to start to understand what issues are we going to be coming up on. We're talking about looking at a brand new way of approaching measuring things at the source term in a way we've never done before. We don't have a network of source term from the stacks available. The technology that's used in stack monitoring currently is typically for health and safety. And we're talking about measuring something with a higher resolution and more isotopes for the need of monitoring. So we're talking about different technology. We're talking about not quite understanding how to work it. So what we did was, started in 2015, we just started to get a group of people together and say, what does it mean? What do we know? How are we going to do this? And it's really to develop methods that require, start to understand what issues we're gonna come across and identify what technical issues we're gonna have to overcome in order to do this. So this was a group of people who kind of came together, and this was our initial idea. It's a very simple idea, where you have an IMS station, which is my little red box. That's all you really need to know about the IMS station. But it's collecting data, and it's in the IMS, and it's sending it to the International Data Center. We just wanted to say, well, if we had a source term and it was collecting data and also went to the IDC, you could potentially link emissions from this facility with an IMS station. And the previous speaker talked about doing exactly that using atmospheric transport modeling. Or if you have more than one isotope detected, you can use the nuclear decay from the various isotopes to link and positively link a source term, a civilian source term that for the most part is irrelevant to the CTBT, to what the IMS is picking up. So this is just a very simple idea of how to do this. On one single cartoon, this is very simple to do. When you get to the details, it gets much more difficult. So our initial objectives for this initial stack sharing thing is really just to, create a data repository. This data has to go somewhere so it can be used, and it has to be done in a confidential manner. And basically start to look at what architecture, what is needed for this data to be used in the future. And because we've never done this before. So we said, well, let's do it and see what kind of problems we come across. The experiment was relatively simple. We had a group of people basically saying what sort of data is currently collected. And different facilities collect different types of data, and it's in different formats, and there's all sorts of information. So first we just said, what is there? And then that is kind of shared with a data team that looked at what was there and said, well, what do we need to do to have some sort of standardized format? What are the type of information we need? What are the type of information is available? You'd be surprised at how many different ways to look at this data there are. And then at the end, of course, we want to be able to use the data for treaty relevant purposes, but that was not part of the experiment that we were doing. We were just trying to see, how do we get data? How do we look at the data with this initial experiment? So what we did was we gathered the data. Currently, we just put a repository that was just on the cloud, basically, initially, because it was very scalable and easy to use. And we did get data from various producers, ranging from raw spectra to process spectra, concentration and air volume data. And we even got some metadata associated with all of this. So we're trying to, and of course, all of these were in all different formats, all different types of process the data. Some data uses spectral fitting to get the data concentrations. Others use region of interest. Some do interference corrections, some don't. I mean, these are the types of things that we ran across in this initial experiment. So initially we said, okay, well, if we're going to do this, what kind of software requirements? What kind of requirements are we going to need for data input, data processing, storage? And so we started to write all of these things, all these things down, which led to where we are now, where we're leading trying to get the ideas together for the Stacks project, which is kind of the next step of the experiment. So experiment part 2, really, where we're, again, trying to collect the data. So the goal of this kind of experiment is to develop technical solutions for stack data collection, what kind of technology to use. I'll talk about that in a bit. Stack data transfer, how do you actually get it to Vienna? How do you do that securely in a way that's so that it can be used for the treaty purposes? And then, of course, how can it be used? We're thinking about that a little bit, but the main part of the experiment is just getting the data. So really, it's how do we get the data? And really, we're trying to develop a global stack network that hasn't existed before. Our main cartoon that we're still using hasn't changed from the initial experiment from 2015. We're still trying to get data from the IMS, data from a source term, and link it all together. So our overall cartoon, the idea is still there. How does it implement it? Again, the cartoon is really nice. It's very simple. We have data coming from various producers going to the International Data Center, and then national data centers can get the source term data for their use in their role in treaty monitoring. So this is the idea of how it would work. Stack data requirements. Here's just what came out of the initial experiment. We were going to collect spectra, flow rate, state of health, QA/QC data. General requirements, again, these are the four xenon isotopes that the IMS measures, so we have those. We defined a 10% uncertainty that we wanted on those. That's open for debate. Even now, people are still arguing about that. Dynamic range is really high, 1 gigabecquerel to 10 terabecquerel. That's actually challenging. So anyway, that's our requirements. This is not going to be a one-size-fits-all solution, mainly because different facilities have different requirements that they're going to put on this. Some facilities will share the spectra directly and it'll go right into this database. Other facilities will not allow that to be sent out. It'll just be processed data. So some analysis will be done and that'll be sent out. Every single facility is going to be worked with specifically, and we're going to have to develop this on a case-by-case basis. But the idea, though, it all goes to here in some sort of organized, standardized way so that it can be used for treaty purposes. So that's kind of the idea. So detector technology, we're planning to use high-purity germanium detector systems. So there's been 2 systems on medical isotope production facilities at IRE and at ANSTO who have used high-purity germanium systems, but there's other systems. INVAP has a sodium iodide-based system, and there's a lanthanum bromide system in Indonesia. So these are different types of technology that we're looking to use it. But based on the experience of the high-purity germanium systems, that's where we're looking to do this, because again, we're going after those 4 isotopes in a very large dynamic range. So lastly, the idea that this data would be useful to understand these detections in the IMS is fairly easy. And if we're going to move this forward, we're going to need this agreed framework for this, for getting the data, standardized technology so that we don't have multiple different ways of looking at it. And then, of course, data confidentiality is going to be key, because a lot of these are coming from commercial facilities that are selling a product, and we don't wish to inhibit that in any way with what we're trying to do. So this is kind of the idea where we're at. We've kind of went through phase 1 and understood a little bit about what's needed. So now we're kind of in the next phase of, well, how are we going to do this, and how are we going to solve these things? What kind of technology we're going to use, and how are we going to deploy that? That's really where we are right now. I'm hoping to come back in SnT 19 and give you some initial data coming off of this, of what we've been able to deploy in the next 2 years. But it's an exciting project. It's challenging. It's not an easy thing to do. So with that, I'll pass it to the chair.
Thank you very much, Judah. So, questions or comments? Yes.
yeah, thank you very much for your presentation. So one comment I wanted to add is that you were talking about the uncertainty of this tech data. I think this is very important because for the ATM challenge, which was presented at WASMIP, so yeah, it was still a long discussion, what is the actual uncertainty of this tech data? And in the end it turned out that we are quite some distance away from the 10%, so it was stated by Anstot that it is at least 20%.
Yes, that's
and
part.
Yeah, maybe we cannot solve this, so to really get 10%, but at least this should be stated in this database. It should be clearly stated what is the actual uncertainty of this data.
Correctly. And there's two aspects to that. One is isotopic ratios, which we should be able to do better than 10%, but absolute quantity is going to be a challenge at 10%.
Okay, I think we have time for one more. Yes.
Thank you for the presentation. It's a very ambitious program. Of those volunteer medical facilities, I mean, are there the major ones or just smaller ones? Because if the smaller ones did not volunteer, if the bigger ones did not volunteer, that will pose a big problem in your source term determinations.
That's a challenging question. The entire process is all voluntary. So we've been in discussions with many producers, both large and small, and there has not been any large objection to doing this. It's the details of how you do it. So we have not heard a no from any producer yet, but it has been, yes, let's talk about exactly how we're going to do that, and that's kind of where we stand. So we will likely, because it's the voluntary nature, we're going to get what we get. So.
Okay. Thank you.
All right. Thank you.
So before we go to the last speaker, I just wanted to remind you we have a small discussion after this. We can continue to ask the presenters specific questions, but also I would like to ask you in the audience to just think about what is missing in terms of data in this context. We have been doing this for 20 years now. Learning from scratch what's in the atmosphere. So what's missing now in the data in terms of measurements, and also do we need to do some other kind of campaigns different from the ones we have done before, also concerning equipment, for instance? Also, what's missing in terms of research, like modeling, atmospheric transport modeling, and isotopic ratios? Just start to think about that, so we can come back to that later. So now, is Silvia Generoso talking about seasonal variability of Xenon-133 atmospheric background characterization and implications for the IMS of the CTBT. Thank you, please.
Good afternoon. I will talk about Xenon-133 atmospheric background due to industrial releases. First, I'd like to acknowledge the co-authors. Pascal Hachim, who has initiated and led most of the studies on this topic at the French NDC. Mireille Morin, Philippe Gross, and Gilbert Lepetit. So the objective of this study is to investigate and describe seasonal patterns of this atmospheric background due to large-scale atmospheric circulation. And in order to do so, we have used a simulation dataset covering 2 years of data. I will briefly summarize the methodology that we've used for the simulation, the main findings, and the validation of this dataset. And then we will focus on the analysis of these seasonal cycles at 3 levels: global scale, IMS network as a whole, stations, and when we will look from simulation dataset and from observation dataset. But first, let's have a look at the global distributions of this atmospheric background, and here is a map of the simulated Xenon-133 atmospheric background in millibecquerel per cubic meter. To obtain these maps, we have considered sources. Only the dominant contributors were considered in the simulations. That is to say, medical isotope production facilities, which are the large light gray circles on the map. We've considered 9 of them. and we've considered nuclear power plants, which are the dark, small circles on the map. We've considered nearly 200 of them in the simulation. And then we've used a dispersion model, the FlexPart model, in order to simulate the atmospheric transport of the releases. And for each sources, we have considered everyday average releases. And for each release, we have calculated the atmospheric dispersion for a period of 30 days. And then the total background of a given day is the sum of the contribution from all the sources and from all the day giving signal to that particular day. And here we are looking at the average over the 2 years period of the study. And the one thing that is obvious about this map is the large spatial variability, which is explained mostly by the location of the source with respect to the atmospheric circulation. And in addition to this large spatial variability, there is a large daily variability that we can see on this movie. Same maps, except every image is a 12-hour average. And you can see a large puff of significant activity concentration from the dominant sources, for example, from facilities in Canada, South Africa, Russia, Australia, and so on. And one thing that is interesting is that we can extract the signal, the simulated signal at a specific IMS station. And here is an example of a time series of 7 months at NOx 49, which is located in the Spitsbergen, Norway. Top plot are the average 12-hour average simulated data. In red, the measurements, but the bottom plot here is carrying a very valuable information to us, as it gives the origin of each simulated peaks, and one color means one source, and you can see that the signal in terms of origin is complex. And for this example, during this period of time, the Norway station has sampled xenon coming from Canada, Belgium, Russia, and this is important to understand that xenon-133, given the proper meteorological conditions, can travel across the hemisphere and be detected thousands of kilometers away from its origins, and along the way meet with xenon from other sources, and at the end what is actually measured by a station is a very complex mixture of various origins. So here just a few words to say that we have validated the simulation using all available measurements at all operational IMS stations during the period of the study. The analysis is fully described in the paper we've published last year, so I'm just saying here that the simulation reproduces the global mechanisms that explain the global distributions of the xenon-133. And based on this knowledge, we're going a step further in the understanding, and the questions here are: is the spatial and daily variability of the atmospheric background that we have just shown explained by seasonal variations of the atmospheric circulation? And can we see these seasonal variations on the IMS network? And in order to do so, we zoom out from considering peak-by-peak analysis or daily averages, and we described time series of monthly averages. Ideally, to address seasonal variations, we would need a long period of time, and this is actually doable with the simulation, as we could easily have only the meteorology, which vary. However, long time series of measurements include also variability of emission, and for this specific issue that we are interested in, this can add additional bias, and this is why we've decided to look at the 2 years simulation data set that we have validated, and we've considered 4 years of measurements, 4 years in order to have enough data to be able to calculate monthly averages. And so we are interested now in trends from these 2 data sets. First, we are going to look at global scales. So here are the monthly average from January from simulation. Here, monthly average for July. And you can notice, for instance, in the northern hemisphere, during winter, there is a large spatial extent of the atmospheric background with respect to July. And the opposite is true for the southern hemisphere, where in July, so winter months for the southern hemisphere, you have a larger spatial extent of the background with respect to January. And so we've translated this observation into an indicator. We have counted the number of grid cells, let's say, on these maps, where the simulated values are greater than 0.1 millibecquerel per cubic meter. And these are the plots that I'm showing here for the 2 years period of time, for the globe, for the northern hemisphere, for the southern hemisphere. And you can clearly see the trends here where for both hemispheres, the spatial extent of the atmospheric background is larger during winter months. And this is what gives this kind of phase opposition between the two hemispheres. And the trends for the globe is driven by the northern hemisphere. So now the question is, can we see that on the IMS network? And so we've redone exactly the same thing, except instead of counting the grid cell, we just considered the location of the IMS stations. And this is what I'm showing here per months. So the red curve is for the globe. The light gray bars, I hope you see them here, are for the network of northern hemisphere station only. And the dark, gray bars here are for the southern hemisphere. And we can notice exactly the same conclusion with predicted detection of the simulated background, which are higher during winter months for both hemispheres, which explain this, again, phase opposition between the two hemispheres, and in red, the global trends. Can we see that in the measurements? And the answer is yes. Here for the globe, for northern hemisphere, this is less pronounced for the southern hemisphere network, as we have less operational stations here. And so now we're interested in looking at the level of a station. So let's start with the example of CNX-20, which is located in Beijing, here, China. These two maps are just to give an idea of the large-scale atmospheric circulation. And these diagrams here is showing the occurrence of direction of wind for the months of December, January, February, so winter months, for 2 years from the NCEP GFS data. So let's say data which are representative of large-scale atmospheric circulation. And so you can see that during winter months, predominantly the winds are from a northwest direction, which is this arrow here. And so the air masses are continental, and upwind of that, we have some of the major producers and sources of xenon 133. And during summer months, you can see that the prevailing winds are rather coming from southeast direction. So here, so from oceanic air masses, upwind, we have no identified sources. So given the location of the station and these meteorological conditions, we expect higher values of xenon 133 measured during winter than during summer. So do we observe that? And the answer is yes. We are here looking at time series of xenon 133 from simulation, from measurement. Each time series is normalized to its own maximum. And you can clearly see the trend that we that we can explain from large-scale circulation. Another thing that is really interesting, we just focus on the bottom plot here, which gives the origin of this xenon, and and this is the same average, and these are the contributors. One color is one source, and you can see here that all year long we have the same contributors. And therefore, here the seasonal variation are for levels of xenon 133. We just move at other stations really quickly of the northern hemisphere, Norway, Mongolia, and Russia, and you can see that we have the same trends. And we are looking at Southern Hemisphere station now, and you can see that we have correctly the opposition of phase with higher New Zealand here and La Réunion with higher activity concentration during the winter months of the Southern Hemisphere. I'm just going really quickly here to say, is there, what is happening for station located close to the equator? And let's take the example of Kourou, French Guiana here, which is located here. And you can see this solid line is the location of the intertropical convergence zone, which is, let's say, the meteorological equator. It's kind of a barrier for air masses, and the interhemispheric transport is not very efficient between the two hemispheres. And the station happens to be located north of this ITCZ during January and winter months of the Northern Hemisphere, and south of this ITCZ during summer months. And actually, in the simulation, we can clearly see the seasonal variations with a change of contributors. Here, the blue color scale refers to sources that are located in the Northern Hemisphere, and which are, for this example, giving the higher values of the atmospheric, of the xenon 133 activity concentration. And from, let's say, August to December, we have contribution from sources from the Southern Hemisphere. And this is just showing a time series over 2.5 years, which we clearly see the cycles and change of contributors. My last example in Ethiopia here, which is a station which is planned, not yet operational, and we can see also the change of contributors with, in this example, the source in the Southern Hemisphere giving the largest activity concentration. And I'm just going quickly to my conclusions, and I will stop here.
Thank you very much for a very nice presentation. So, do we have any questions, comments on this particular presentation right now? Please, the floor is open. I can't see anybody. Okay, so thank you very much for that. So, so now we have time for a short discussion regarding this topic. And like I said before, we have been doing this for quite many years now, 15, 20 years, in this context of verification of the CTBT. And when asking then the question, what is missing? Well, at least what's on my mind is what is missing with respect to being able to do a good job regarding verification. So you can always learn a lot about the background in the atmosphere, and that's very, very good. But if you focus even more on what's needed for a verification purpose, a verification mission, I think we can focus on that a little bit. So do we have any thoughts on this? Regarding the data we need, the modeling we do, or the campaigns we are conducting? Yes.
I think we're doing verification. So from a verification point of view, we have to be able to, so the problem is we can see a measurement in the network with, once upon a time maybe we thought that just seeing xenon would be significant, but we've learned over 20 years that it's not necessarily so. And we're learning how reactors and how medical isotope production gives certain background patterns in our network. But finally, I think we need to be able to recognize what xenon ratios could be indicative of a treaty violation. And see, once such a detection has been characterized as a possible violation, we need to be able to see, is there a source, a civilian source that where it could come from. So I still think the backtracking or the location of a source given a detection at one or more stations with a significant fingerprint, so significant in the sense of being a possible violation of the treaty in the multi-ratio isotope correlation plot or something like that. So to me, the backtracking and sort of narrowing in where could the source be, I think that's still the most important, probably. And then, if we do find a possible source, of course, to know, was it emitting at the time? So still, I think the stack emission data and all this is going to be very helpful. But yeah, just seeing xenon 133 sometimes, so X% of all days during a year we see xenon 133 from this or that. It's not in itself. I mean, with verification, we're looking at a unique event. We see something. We need to say something about it. So backtracking individual detections, what are the possible sources, and where they're emitting. I think that's the way we have to. So it comes down to atmospheric, so location, atmospheric transport modeling, and locating sources. So that's the uncertainty of ATM and so on that we're coming to. Okay. I think that's the most important research topic.
So what do you think is missing? Where do we need to spend more effort?
Uncertainty of ATM, to know how good is our location. So how good is the location that we can do based on ATM and network detections in the IMS.
Okay. I think I saw a hand down there. Yes.
Thank you. One of the things that I think is really important to remember is the hits that we get in the IMS came from somewhere. Because they came from somewhere, the challenge is identifying the source for every single hit. That sounds daunting, but I do believe ultimately that that is the direction that we should be going in. So the earlier individual talking about backtracking, that's critical. But it also is critical that of those that we know where it came from, that we start building up the database to say, on this day, this station saw something from a power plant, a medical isotope production facility, et cetera. We have to build up that, that knowledge base. Once we do that, I believe that it will be a lot easier to say, what are the ones that don't fit? And what do we need to do some more? And we have thousands of files that we can do this with. And although first cut, it may not be very good, it begins to allow us to manipulate the big data that we have to finally come up with where did a single detection come from, and what probability do we have that it came from that facility, that location, that nuclear reactor, et cetera. And then we can continue refining it. But we haven't really done that. We've only looked at the ones that we're cared about after a nuclear test. All the rest of them, while they may be disinteresting, are actually pretty interesting. Lots of them, let's categorize them and put them in a bin. So that's all.
So I guess you're saying that we need to do more with the data we already collected, right? Yeah. Yes, please.
Thank you. In fact, I come back to the previous comments also. I think understanding the xenon background is still quite important because, in fact, yeah, in an ideal case, you would have 4 isotopes of xenon. You could easily then start discriminating. But most of the case, you only have 1 isotope, and that's the xenon 133. And if you don't understand the background, then you just don't know from where it comes. And I think that's the main issue. But I still agree also that backtracking is still quite an important aspect as well.
Yes, in the front here. Oh, yeah. Here. No,
Yes, I agree with the last intervention. So what we really need is a very sophisticated way of estimating that background. The same as they do in weather forecasting, they combine a model with observation, they produce an objective analysis, and then they have a very high quality analysis. And to do the same for xenon, we need, as it was mentioned earlier, a source term. We need all the important contributors. We need to use an ATM model to produce a forecast, to combine this short-term forecast with observation, and to correct this as you go along. So ultimately, you will produce a very high-quality xenon analysis, and this will really contribute to identify real events. And the other aspect for uncertainties, we at CTBTO, we are exploring the possibilities of applying a ensemble prediction system approach to ATM so that we can estimate the uncertainty. In every forecast there is an uncertainty, and you need to be able to estimate it. And this uncertainty can be used also in the analysis, because when you have to assimilate a new data, you have to know how confident you are in the observation and how confident you are in your forecast. So we really need the uncertainties both in the source term and in the forecast of ATM.
Right. So do you have Anders? Do you have?
So obviously, I don't want to come across as trying to defend some extreme view where we should not study a background. Obviously, we should. Obviously, it's very interesting, and obviously, it's going to be useful. It's only that keep in mind what you saw. I think it was in Silvia Generoso's presentation. Several sources mixing all the time. So this complexity of the background. So there's a high risk that for many, or maybe most, detections of one or two isotopes, we will just never be able to say other than this. It's a mixture of several sources, which is quite likely this time of year or something like that. But what we need to be prepared for is today we see one detection or a series of detections with a unique signature that we never saw before, and it's therefore very unlikely to be a mixture of several civilian sources or so. And then we need to be able to track it and find where it came from. But of course we should study the background. So, thank you.
Okay, thank you very much for this. I think we got a few valuable points here. We stop here, the discussion, and we go on to the next, to the last point on this session's agenda, and that is the poster preview session. So I ask all the poster preview presenters to join me up here for your 1 minute presentations. I hope you remember your number. Okay. Okay, so I guess we can start this now. Sure. Okay. Okay. That was. So we are running now. Please.
Okay. This is a poster that looks into the question whether the coincidence of a detection of the most frequently observed xenon-133 and the most frequently observed iodine isotope 131 has any relationship in the isotopic activity ratio that could possibly indicate a source. So we were looking at simulations describing nuclear reactor releases and the releases of nuclear tests, and also we looked at reported data, and the results you will find at our poster. Thank you very much.
This one? No presenter? Okay.
Hello, good afternoon. This poster is about the new research reactor that is under construction in Argentina. Nuclear Regulatory Authority released in 2014 the license for this new facility. This reactor will be used to produce molybdenum-99 and studies about neutron beams and material and fuel irradiations. The expansion of the production of molybdenum-99 from 900 per week to 400 will allow to Argentina consolidate as a big producer. In 2020, we'll release a license for the production. Thank you. You can visit my poster.
Good afternoon, everyone. Argentina was the first country in the world that changed the enrichment of uranium in its radioisotope production process. In 1985, the radioisotope production plant from fission began the commercialization of molybdenum-99 irradiating high enrichment uranium targets, and in 2002, it was replaced by low enrichment uranium targets. The poster shows the conversion, a brief description of the production process, and the improvements to reduce emissions of radioxenons to the environment. Thank you very much.
Good afternoon. Radioxenon trap prototype has been developed by SCK and is currently under testing at the IRE in Belgium. This is the phase one of our project, so the trap is under testing and evaluation. Separately, SCK is developing additional design studies for 3 other nuclear facilities based on characteristic features of the operational process. And last but not least, we are preparing a controlled source experiment with field measurements around the IRE supported by high resolution ATM. Thank you.
Hello. We did some reactor simulations on xenon isotopic ratios, and we are lucky to work together with Matthias Englert and Christoph Pistner at Darmstadt. Christoph Pistner, one of the original co-authors of the original Kalinowski paper from 2006 for the 4-isotope plot, and we did some parameter sensitivity studies, how the ratios develop under different conditions, so different fuel types, reactor types, and operational status. The results were not too exciting. They are all on the safe side, the ratios in normal operation. So we had further look on release pathways under not normal operational conditions. So something like incident during refueling or something like that, or after restart. Come to the poster. Thank you.
Good afternoon. So in this poster, we are presenting the result with regard to radioxenon mitigation, which was performed under the European Union Council Decision 5 project in support of the CTBT. So for this project, we are presenting the result. Part of this was the investigation of xenon adsorption material to be used for such a xenon trapping system. Then we also perform design studies to optimize the xenon trapping system, which resulted in a compact, flexible, and mobile system. And at the end of the project, we constructed a real prototype and tested it in our laboratory setup. So if you want more detail, if you want to discuss it, please come visit our poster. So it's T2.4 P10. So thank you. And in this poster, it's a different study. We are presenting the result of a study we did where we developed a baseline radioxenon emission inventory from civilian sources, so from nuclear power plants and also medical isotope production facility for the year 2014. We did it for the 4 xenon isotopes, so the 4 CTBT relevant isotopes. And we characterized the estimated radioxenon background at different IMS noble gas location. And of course, we compared also the result of the estimation with the observation during the year 2014. So again, you're welcome to visit our poster and discuss it with us. Thank you.
So this poster is about a software tool. It's actually a prototype that we developed at the CTBTO. And the software is called SIMPAX, which stands for simulating the impact of xenon from civilian sources on IMS stations. As you can see on the left side, this is basically the input window where the user can define the source term in terms of emission facility. And so far we already have medical production, isotope production facilities and nuclear power plants included in the default configuration. Then the software works for all xenon isotopes, and then the map on the middle is actually the impact that is materialized in terms of colors. Thank you.
Good afternoon again. In this poster, we are explaining what we are doing with a large set of stack emission data files that we have received from the Inuki facility, from BATEC, and we are also addressing quite carefully all the confidentiality issues that were raised by medical isotope production facilities. If you want further details on this and discussion on this, please pass by the poster. Thank you.
Good afternoon. My name is Mariana Ditada, and I work in INVAP in Argentina. The poster is about the startup and calibration of the new stack air effluent monitor. It's a winter in southern hemisphere, the snowman finally brought us the chambers, the measuring chambers, so we are ready to start the assembly of the new monitor. So if you want to see a little bit more about that, we did some measurements in a real stack environment, and we have the detectors are already characterized. So come and see this poster, and there's another one that is in the same section, and it is the P4, which is the history of INVAP monitors. Thank you.
Good afternoon, everybody. Based on more or less 10 years of IMS radioxenon measurement, analyzed by Swedish, Canadian, and French NDCs, we show that new flag can be used by EDC to substantially improve the categorization scheme. So, see the poster for more information. Thank you.
So in this poster, we are summarizing the xenon background at the IMS stations, which are currently 25 systems in the IDC operations. And this is based on 5 years of reviewed data from the IDC operations. And so please take a look at this where more is compiled.
Good afternoon. My name is Lucrezia Terzi from SCK. This work is a cooperation between CTBTO and SCK on the potential use of xenon dataset. We reconstructed a global xenon 133 concentration map and compared the simulation minus the observed concentration of xenon and analyze the residual and see what is the feedback that can be provided into the global emission inventory. Thank you very much.
Good afternoon. My name is Eduardo Nasif. I come from INVAP, Argentina. This poster is a report on WASMIP 6, the workshop on signatures of man-made isotope production, that joined about 80 participants, more than 60 contributions coming from 27 countries. It was held in the Argentine city of San Carlos de Bariloche from November 28th to December 2nd, 2016. And it was the first WASMIP conference held out of Europe. There were quite a number of relevant discussions, roundtable, and interesting conclusions. So if you want to know more about this meeting, please come and see our poster.
Distinguished colleagues, good afternoon. My name is Giuseppe Ottaviano from the ENEA, the Italian National Agencies for New Technologies, Energy and Sustainable Economic Development. Our work is about the xenon radioisotope signature from nuclear power plants. We investigated the xenon radioisotope production as a function of a nuclear power plant rapid power variation. The investigation was made through a parametric analysis using the scale 6.1 origin S code, and we investigated the impact of this variation on the discrimination of the related isotopic ratios with respect to the threshold of the corresponding screening flags. You can see some example. From the left, an example of the time trend of the reactor cycles, then an example of the time trend of the activity. Please visit our poster in the Winter Garden room. Thank you.
Okay, so thank you very much for that. So I just wanted to say that since I wasn't quick enough to present the first poster, which actually was my own poster, you're welcome to visit that one too. It's number 1. It's about an intercomparison experiment between a SONA 2 and a SONA 3 system. So it's quite interesting. We have a 6-hour time resolution versus 12-hour time resolution measurements on the same air. Please come visit that one too. Okay, by that I guess we are done with this session. So I thank all the speakers again, and yeah, thank you.
A big effort to get people lined up there. What should we do? Do you know who the first one to are? Let's see. Let's see, we're 2.3. We need. Oh, Strushkova. Is she here? Anastasia Strushkova. Let's see who. It's not going to work unless they line up.
No, that's.
Go over there and see if
I'll make an announcement. I'll make an announcement.
Okay, so if there are any more radionuclide experts who wish to leave before the next session, then I would encourage them to do so, and then we will begin the next session. Yeah, no, the highlights. Recognize them. Okay, so a couple of them down there. Okay, so welcome to session 2.3, Seismoacoustic Sources in Theory and Practice. My name's Bob Pearce, and on my right is Paul Richards. Most of you probably know both of us. You will have noticed that there aren't any oral presentations in this session, that it is simply a poster preview session. And by way of explanation, we did have a number of good oral presentations, but we thought that they belonged better in other sessions. In particular, several of them belonged better in T2.1 treaty-relevant events. So that is where you will go and find them. So before I pass the floor over to Paul Richards, I just remind those of you who have poster previews to start to get yourselves lined up on the side of the room in the customary manner. But then I will ask Paul wishes to say a few words, so I'll hand over to Paul.
Thank you, Bob. So let the record show we have 15 posters in this session, of which 8 are associated with poster previews that we can expect to hear in the next few minutes. I am tempted to write a dreadful limerick introducing everybody, but I will suppress my instincts in this matter and simply get out of the way. My thanks are to the people who generated these posters. It's a lot of work, and to travel a long distance to give presentations to a complicated audience. My sentiment basically is to say, let's roll.
Okay, and in case I forget to say this after the poster preview session, do make sure that you do come to the poster session, which for our topic is in the Festsaal at 1600, and we will see you all there. So I think we can begin.
Obviously, I'm not Anastasia. She's tied up with the next few experiments she's setting up. That's part of the study. But for 20 years, many seismologists in the verification community believe that chemical explosive yield and the nuclear can be simplified by a factor of 2 or something like that, based on a very good data point. Now the community started to understand and recognize that actually there are many other factors. Of course, the velocity of detonation, but then also the temperature of the explosive, and also the amount of gas generated. So this team is conducting empirical study to document those effects, plus the emplacement conditions. So this is poster number 1. Thank you.
Good.
In this poster, good afternoon. In this poster, we present velocity data from a series of buried chemical explosions, which we think help to identify some possible sources of shear energy that might show up in seismic measurements further outfield. We tie some of that data into directional motion as measured by surface photogrammetry measurements from both pre and post test to help us to correlate the data. Finally, a lot of the mechanisms that we identify are related to some finite element numerical modeling that we've done to support our analysis. Thank you.
Hello, my name is Celso. In this poster, I present methodological developments for estimating seismic moment tensors with uncertainties and applications. The figure on the left shows an example estimation for the Hoya nuclear test in the Nevada test site. The figure on the right shows an uncertainty analysis for this event. On the top is the positive isotropic solutions. At the bottom is negative isotropic solutions. In the center is a double couple. The best solution for the Hoya event is in the positive isotropic region. For questions or details, please come to my poster. Thank you.
Well, I'm Chandan Saika from Air Force Technical Application Center, United States. In this poster, we developed a technique in which we equalize waveforms from events like 2 explosions close by or 2 in different sites. And we have applied 2 methods. And if you come to our poster, we'll see the mathematically how we proceed. And you will see application of this whole technique with respect to the data and using both theoretical source time function as well as empirical source time functions. Thank you.
Good afternoon. My name is Paulina Bittner, and I am representing ITC analysts in CTBTO. We have a poster about events detected by the Indian Ocean network of hydroacoustic IMS stations. Until December last year, we had only 2 stations in this area, and in January, 3rd station installed across the islands has joined the network. So all of them are hydrophone stations, which is very interesting. This map shows REB events which we detected since the HO4 came into operations. If you are interested about other information, please come and see our poster. Thank you very much.
Okay, so in this poster we present an analysis of seismic and hydroacoustic signals from a series of US Navy trial explosions detonated near Florida. These explosions are associated with testing US Navy ships, and we can use these signals recorded on the IMS for location, characterization and yield estimation. One of the interesting observations is that the bubble pulse signature is quite a lot weaker on the hydroacoustic data when compared to the seismic data. So please come on and have a look.
Good afternoon. Seismoacoustic effects of shallow, moderate Hubsagugi earthquakes were investigated. The infrasound signal was recorded by station Torre at the distances 175 kilometers. High effective velocity of infrasound signals indicates that it was caused by the secondary south. The position of secondary south is defined on the northern slope of Hamardaban Ridge, and the most probable mechanism of formation of sound signal is the interaction of surface waves and topography of region. Thank you for attention.
Once again, in this paper, we developed a time domain source time functions, which we call it TDSF, for exposons at elastic radii. And this one was motivated by the observed data from chemical as well as nuclear explosions that were recorded very close in. We observed that below corner frequency spectra is going a little higher, and we wanted to seek out why it is happening. In that regard, we found that a near field term, if we include it in our existing solutions, it explains the spectral characteristics. If you come to my poster, I'll be able to explain the math as well as more data, how it has been modeled, and other factors like scaling, as well as reason why source time function formula, in that some of the parameters need to be adjusted with respect to Miller-Murphy source. Thanks.
So thank you for all of these presentations, and I can only encourage the audience to first recognize the great breadth of subject matter in this special session on seismoacoustics, and to take the time to see the actual posters, not only of the 8 which we've just heard introduced, but the other 7. So we expect 15 of these posters to be on the screens over the next few days for your perusal.
So thank you very much. We'll see you at 4 o'clock.